All right, so here's the packet. We can see here our state of standards and then our standards-based objectives below. And this is where the notes start. So when you're looking at a substance formula, you can determine whether or not it's an acid or a base kind of easily using what's known as Arrhenius acid-base theory. To identify something as an acid, it would start with H. So it has that hydrogen ion present. So HCl, that is an acid. What that means is it has a pH of what we call less than 7. pH 7 is neutral. pH less than 7 is something that is acidic, and pH greater than 7 would be something that is basic. Another way to say basic is alkaline. So if we take a look here, HCl, that would be acidic. Its pH is less than 7. Now, if a substance has what's called a hydroxide or OH, a polyatomic ion, OH negative, then it is a base. Other bases exist for this section. This is the only thing we care about. So we see here calcium hydroxide. We have that hydroxide there. So that is a base. Go ahead through there and determine whether or not each is an acid or base. I'll give you a minute. We'll grab a drink. All right. We have an H in front of both of these, so they are acids. We have an OH to back of both of these, so they are bases. We have an H in front of both of these, so they are acids. Is that easy for Arrhenius acid bases? Here's something that needs to be memorized. These are known as the 6 strong acids: hydrochloric, hydrobromic, and hydroiodic. If we look where they are in the periodic table, chloric, bromic, iodic. There are the 3 halogens right here. They are 3 of the strong 6. The other 3 are the 8s: nitrate, sulfate, perchlorate. Right? So if we take a look, nitrate, perchlorate, and sulfate. Notice sulfate has a -2 charge. That's why it has 2 hydrogens, because each hydrogen, if you recall, has a +1 charge. So nitrate, perchlorate, and sulfate is sulfuric, perchloric, and nitric acid. 5 of the above, 5 of the 6 are considered what we call monoprotic, because there's just 1 H on each. And that makes sense because Cl has a -1 charge. There only needs to be 1 H. Bromine has a -1 charge, so 1 H. Iodine has a -1 charge, so it's 1 H. Nitrate and perchlorate, -1, so it's 1 H. Sulfate, -2, so there's 2 H's. That is diprotic. Remember that a hydrogen ion is just a proton because it's lost the electron. So that's why we say protic. Hydrogen ion is just a proton. So it is diprotic because it has 2 hydrogens. What would something that is triprotic be? It would have how many hydrogens? 3. H3PO4. Now, this is not one of the strong ones. Now, what does it mean to be strong? A strong means that it ionizes completely. This does not ionize very well. Phosphoric acid, this is in Coca-Cola, right? Malonic acid, that's what makes sour gummy guys sour. It's also a weak acid. Hydrochloric acid, that's the acid that's in your stomach. It's strong, right? Your stomach has to create this big, thick slime layer so it doesn't actually dissolve itself. So these down here are the 6 strong bases. Those are the 6 strong bases: lithium, sodium, and potassium, iridium, and cesium. These are all of the first 1A metals, the alkali metals. So lithium, sodium, potassium, rubidium, cesium, hydroxide. And then calcium hydroxide is also considered a strong base. Again, that means that they ionize completely. You don't remember what ionized means? That means that they break apart. Rubidium hydroxide breaks down into rubidium and hydroxide. That's ionizing. It ionizes. It forms the ions when it's dissolved in water. Most of these are considered monobasic, except for calcium hydroxide, which is dibasic. Tribasic would be like aluminum hydroxide. So if we take a look here, these are the properties of acids and these are the properties of bases. So acids feel wet to the touch. If you were to taste an acid, it would taste sour, like citric acid and a lime. It reacts with metals. They turn what's called litmus red. Litmus is an indicator. The pH, as we said, is less than 7. Now, this is something new. The hydrogen ion or hydronium ion concentration is greater than the hydroxide ion concentration. They have more H3O plus. Now, let me show you what this means. For example, if I take HCl and I add that to water, that will make hydronium. The extra H plus will attach to the water and the Cl negative will float away. This is what makes something acidic. This is known as the hydronium ion. Basically, instead of H2O, it's H3O plus. And last but not least, acids will neutralize bases. Bases, on the other hand, they feel slippery to the skin, for example, like soap. They react with magnesium to precipitate. They turn litmus paper blue. Their pH is greater than 7. And their hydroxide ion concentration is greater than their hydronium ion concentration. And they neutralize acids. So go down through here and put A for acid, B for base, or X for both. I'll give you a second. Yeah. For the rate quiz? Yeah. Which one? Was it like the last question? Dun, dun, dun. Bum, 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 bum. Oh, I see. Now it was based on it's just based on the idea that if the temperature goes up by 10 degrees, then the rate doubles. Yeah, 0.004 moles per liter. So it's at per hour at 20 degrees Celsius. Then you go up to 30 degrees Celsius. So you would just double it. Or if we went from 20 degrees Celsius to 40 degrees Celsius, then you would double it twice. All right, let's take a look here. It feels smooth and slippery. That is a base. Has a sour taste. That's an acid. Stings in an open wound. That would be both of them. Reacts to metals to form hydrogen gas. That would be an acid. Has a bitter taste. That's a base. Base tastes bittery. Conducts electricity. That's both of them. Last thing we want to do today is we want to be able to name acids and bases and be able to write out the formula for them. So if we take a look, if the anion ends in IDE, for example, fluoride, chloride, bromide, oxide, all of these, then we put hydro in front and we change the ending to ic instead of IDE. So here we have Br, which is bromide. We put hydro, brome, and change the ending to ic, hydrobromic acid. Here we have cyanide, which is a polyatomic ion that can be found on the back of the periodic table. So that is cyanide. We change the IDE to ic, and we put hydro in front of it, so it becomes hydrocyanic. If it ends in ate, like sulfate, nitrate, chlorate, then we change the ate to ic, and we add acid to it. So chlorate becomes chloric acid. Sulfate becomes sulfuric acid. We take the ate off, and we add IC at the end. Nitrate would become nitric acid. If it ends in ite, sulfite, nitrite, right? Chlorite, hypochlorite. We change the ite to an us. Chlorite becomes chlorous acid. Sulfite becomes sulfurous acid. To name bases, we basically name the cation. And then the ending is hydroxide. Hydroxide has a -1 charge. So whatever the charge of the cation is, that's how many hydroxides you're going to need. So here we have ammonium hydroxide. Hydroxide is OH. This is a base. So we need to figure out what ammonium is. We take a look here. Ammonium is NH4 with a +1 charge. So ammonium is NH4. Hydroxide is OH. We got a +1 and a -1, which cancel out. The formula for ammonium hydroxide is NH4OH. Hydrochloric acid. Well, hydro means that it used to end in IDE. So it used to be chloride. Chloride is Cl with a -1 charge. How many hydrogens are needed to balance out a -1 charge? 1. HCl. Perchloric acid. That means it used to be perchlorate. Perchlorate is ClO4 -1. With a -1 there, we need 1 hydrogen to balance out the -1. Lead-4 hydroxide. The fact that it says lead and then the Roman numeral 4, if you recall, tells us that the lead has a +4 charge. So if hydroxide is -1, how many hydroxides will we need? We will need 4. Lead-4 hydroxide. That's old stuff. We learned that last semester. Balancing those charges. What if we are given the formulas and we have to go to the name? So we have hydrogen bromide. It ends in IDE. So that means we need hydro. Brome, we're going to change the IDE to ic, hydrobromic acid. Or here we have NO2. I'm not sure why that's so small, but it does say NO2 there. NO2. NO2 is nitrite. So it ends in ITE. That means we keep the nite, but instead of ite, nitrite, we change the ite to us, and that becomes nitrous acid. Here we have SNOH, so that is 10 hydroxide. 10 is not in group 1A, 2A, silver, zinc, or aluminum, so it does require a Roman numeral. In order to find the Roman numeral for 10, we take the charge of hydroxide, which is -1. We multiply it by how many hydroxides there are, which is 2. Then we divide it by how many 10s there are, which is 1. So 1 times 2 divided by 1 is 2, which is 10,2 hydroxide. The assignment for the rest of this period and till tomorrow is to finish this down to here. Naming those acids and those bases. We'll go over that tomorrow with questions. I will keep the Zoom on, so if you want to ask questions during the Zoom, you're more than welcome.